For any given random variable, we are often interested in their properties, and the two numbers are often used to summarize the probability distribution for a random variable, the mean and the variance. The mean is a measure of the center or middle of the probability distribution, and the variance is a measure of the dispersion or variability in the distribution. If a discrete random variable x has a range of x1, x2, x3 all the way to xn, the mean or expected value of the discrete random variable x, denoted as mu or e of x, is given by the following equation. Well, the xi representing the individual numbers in the range, and the fxi is the probability mass function evaluated at xi. So you can see that it's a summation of all the xi's multiplied by is probability mass function, and you can consider the mean of random variable x as the weighted average of the possible value of x with weight equal to the probability. Well, the weight is equal to the probability here. Let's look at one example. The number of messages sent per hour over a computer network is defined as random variable x. It has the following distribution summarized in the table here. So the number of messages sent per hour range from 10 to 15, and the corresponding probability for each one of the values that are possible for x are listed in the second row. And for random variable x, we want to determine the mean of the number of messages sent per hour. Or sometimes you can simply just say we want to determine the mean or expected value of variable x. To do that, we simply just use each individual possible value of x multiplied by the corresponding probability mass function evaluated at that value, and do the summation for all the possible value of x. So you will end up with the expected value equal to 12.5. What that suggests is that in the long run, we expect the average number of messages sent per hour to be 12.5. The second number that I often use to summarize the property of random variable x is the variance of the random variable. It used to express the dispersion or variability of the variable. Again, if we have a discrete random variable x with range x1, x2, x3, so on, so forth, the variance of the discrete random variable x, denoted as sigma square, or the v of x, is given by the equation here. So the variance of x is the squared distance from the variable to its own mean. So the third term in this equation, that's the definition of the variance. And this variance can also be calculated using this equation. It's also equal to the expected value of x squared minus the square of the mean. And oftentimes the second expression is more convenient for computation, where the mu is the mean or expected value of x. And from the variance, we can derive the standard deviation, which is simply just the positive square root of the variance of the random variable x. And you should be cautious that the expected value of x squared is not equal to the expected value of the x squared. These two terms are different. So the first left-hand term, e of x squared, is after you take the operation of expected value, then square the expected value. While the second term on the right-hand side is the expected value of a function of x, while the function is the square of the x. And to expand the definition of variance, we can get the formula here. So basically you have to take every possible value of xi minus the expected value of the random variable, square that difference, then for each one of them multiply by the corresponding probability mass function, and you sum all the items for all the i's. And if you use the second expression, then you should square each individual value of x multiplied by the corresponding probability mass function. After the summation is done, you should take the square of the expected value mu square out. You get the variance of x. So these two are equivalent. You can choose either one of it. Let's still use the same random variable we used to calculate the mean to illustrate the way we calculate the variance. Here we want to determine the standard deviation of the number of messages sent per hour. To do that, we first need to calculate the variance of the variable x. And here we simply just let's first use the first method. So each individual possible value of x, you take that, and before you calculate the variance of x, you have to first calculate the mean. So the mean we already determined to be 12.5 from the previous example. So use each individual xi minus the mean, take the square, then multiply by the corresponding probability mass function for that particular value of xi, and do the summation for all the terms. You will end up with the variance. And here the variance is equal to 1.85. And if you decided to use the second approach, here's how you do it. So here you don't have to do the subtraction from each individual value of xi from the mean of the x. Instead, you just square each individual value of the xi and multiply by the probability mass function. But make sure you remember to minus the mu square at the end. And if you use the first approach, you don't have to do this. And both approach, you will get the same answer, 1.85, as the variance of the random variable. In the last step, you have to take the square root of the variance, get the standard deviation. The standard deviation is equal to 1.36. So the unit of the standard deviation is the same as the variable itself. So it's in the same unit, while the variance is the square of the basic unit of the random variable. And this is a graphic illustration of the meaning of mean. So for any mean for a discrete random variable, you can treat the probability mass function as the weight applied on a very thin beam, where the beam is the real axis, and the loading or the force is acting on all the possible values of x, and the mean is the balance point. So you can see that these figure A and B shows two different probability distribution, but they share the same mean with totally different distribution, and the left hand side obviously have more dispersion, therefore the variance is larger. And in this case, the left hand side figure and the right hand side figure also shows drastically different distribution, but they have the same mean and variance. So this tells us that the mean and variance alone cannot fully determine the distribution. So we still, if you want to know the full distribution, you still need to know the probability mass function for a discrete random variable. So even though two distributions can have the same mean and variance, but they may look very different. The last topic is about expected value of a function of discrete random variable. So if we have x as a discrete random variable with a probability mass function f of x, then for any given function h, we have the expected value of h of x is simply equal to the summation of h of x evaluated at all the possible value of x multiplied by the probability mass function, and have a summation for all the terms. And for a special case, well, h of x is simply a constant multiplied by x plus a constant, so it's a linear transformation of the x. Then we have the conclusion that the expected value of the h of x, which is the expected value of ax plus b, is simply a multiplied by the expected value of x plus b. Well, for the variance of the same function ax plus b, the variance has nothing to do with the constant b, but it's going to be equal to the a squared multiplied by the original the variance of original variable x. And the specific example will be illustrated in the next session.